Fertile hatching eggs don't start in the hatchery. They start in breeder houses, where carefully selected parent stock produces eggs. It's engineered for one outcome: fast-growing broilers with predictable feed conversion. Those breeder flocks are managed on precise lighting schedules to control egg production, and their nutrition is tuned for shell strength and embryo viability. Because a weak shell means higher water loss in incubation and a weaker chick at hatch. Once eggs are collected, the countdown is about biology and logistics. Eggs are porous. The embryo is alive, but paused. And temperature determines whether development stays suspended or starts prematurely. In the US megasystem, eggs are moved into clean, chilled egg rooms and shipped in temperature-controlled trucks, typically held around the mid-50s to low 60s Fahrenheit, to slow embryo growth without causing cold injury. Storage is not just cold, it's controlled humidity too, because eggs must retain the right moisture to support the embryo's air cell formation later. At the hatchery receiving dock, traceability locks in. Each pallet is scanned by flock, age, and lay date. Because hatch rates and chick quality are tied to breeder age, storage time, and transport conditions. A hatchery running millions of chicks per week operates like a production plant with biological inputs. Every deviation in egg temperature history becomes a measurable loss in hatchability and uniformity. Before incubation, eggs are sanitized, but that step is engineered to protect the shell's defenses. The shell has a cuticle that blocks bacteria, so harsh washing can strip protection and drive contamination inside. Many modern hatcheries use calibrated disinfection methods like controlled fogging with approved agents, UV exposure, or ozone in ventilation systems. Aiming to reduce surface microbial load without soaking the shell, air handling is designed for positive pressure and filtration, because hatcheries fight airborne contamination continuously. Eggs then go through dewarming, and this step looks simple, but it's critical. Cold eggs placed directly into warm incubators, sweat, condensation forms, and that moisture becomes a pathway for bacteria to cross the shell. So eggs are staged in tempering rooms where air temperature ramps up gradually until the egg internal temperature is stable. Hatcheries track eggshell temperature because it's more predictive than room temperature. The embryo responds to shell temperature, not the thermostat on the wall. Incubation starts in the setter, a massive climate-controlled cabinet that's essentially a hide-and-seek life support system. Setters hold tens of thousands of eggs per machine, stacked on trays with forced air circulation that must be uniform from corner to corner. The target is to keep every embryo at nearly the same thermal and moisture conditions, because a hatchery doesn't want early and late chicks. It wants a tight hatch window so processing and transport are efficient. Temperature. Control in a setter is tight because embryos generate heat as they develop. Early on, the egg absorbs heat. Later, the egg becomes a heat source. Setters compensate with zoned airflow, variable speed fans, and automated dampers that mix fresh air with recirculated air. Sensors monitor temperature and humidity continuously. Cayenne systems calculate embryo heat output indirectly by tracking exhaust temperature and co-concentration. That CO matters because it's a signal of metabolism and also a control lever. Small co-adjustments can influence development rate and synchrony. Humidity is controlled, because eggs must lose water at a predictable rate. During incubation, the egg gradually evaporates water through the shell pores, enlarging the air cell that the chick uses for its first breaths. Too little water loss and the chick can drown internally at hatch. Too much, and the chick dehydrates and hatches weak. Hatcheries verify this with egg weight loss targets, often weighing sample trays over time, because a specific % weight loss is the most reliable indicator that humidity and tenacity, ventilation, are correctly balanced. Turning is another engineered necessity, not tradition. Egg trays rotate back and forth on a schedule, usually many times per day, to prevent the embryo from sticking to membranes and to promote proper vascular development. Turning angle, frequency, and timing are programmed into the setter's controls. Because missed turning shows up later as malpositioned chicks and poor hatch rates. In mega hatcheries, turning systems are built for reliability under continuous load, with redundant motors and alarmed position sensors, because a few hours of turning failure can ruin a full setter's output about a week into incubation. Many operations candle or scan eggs to remove clears and early dead embryos. In a high-throughput hatchery, candling is automated. Eggs pass under bright light or imaging systems that detect embryonic development by light transmission patterns. Removes are not just waste reduction. They are contamination control, because dead embryos can become bacterial factories under warm conditions. Removing non-viable eggs improves air quality and lowers the risk of exploders. Eggs that burst under gas pressure and spread contamination across trays. In the US, in novo vaccination is common and highly mechanized. Around day 18, robotic needle systems inject vaccine into the amniotic fluid or embryo with precise depth control. The machine's value is consistency. It vaccinates tens of thousands of embryos per hour at controlled dose volume, reducing labor and improving uniformity compared to manual chick vaccination. Needles are sterilized, monitored for blockage, and replaced on schedules because any contamination at this step becomes a hatchery-wide risk. Asterisk around day 18, eggs are transferred from setters to hatchers. This is the handoff from development control to hatch control. Transfer systems move trays into baskets that allow chicks to hatch and drop safely while keeping shells and fluff contained. Hatchers run at slightly different humidity and airflow settings than setters, because now the goal is to support pipping and emergence without drying. Membranes. The hatcher environment is designed to manage a surge of biology. As chicks pip internally, they start breathing air from the air cell, then break the shell and breathe room air, and CO levels can rise quickly. Ventilation rates are engineered to maintain oxygen while keeping humidity high enough that membranes don't turn leathery and trap chicks. That balance is why hatchers have powerful, controllable airflow systems, and why hatchery rooms are designed with separate air circuits to prevent cross-contamination between machines. The hatch window is a logistics problem disguised as biology. Chicks that hatch too early sit longer without feed and water and can dehydrate, while chicks that hatch too late miss processing and shipping schedules. Modern hatcheries manage this with precise incubation profiles, egg temperature mapping, and flock-specific programs. Some operations use single-stage incubation where all eggs in a setter are the same age, allowing the machine to follow an optimized curve. Others use multi-stage incubation where different aged eggs share a machine, trading optimal control for energy efficiency because older embryos' heat helps warm younger eggs. After hatch, chick processing is a rapid controlled flow designed to protect fragile birds and meet biosecurity requirements. Chicks are separated from shells and debris on conveyors with calibrated airflow that pulls away light fluff and shell fragments. Any weak or non-viable chicks are removed by trained technicians because early culling improves flock performance and welfare by preventing suffering and reducing disease pressure. Vaccination at DOL stage may still occur, often as spray vaccination or gel droplet systems. Spray droplet size is engineered so the vaccine lands on eyes and beaks for uptake without chilling the chicks. Gel systems help ensure each chick pecks the gel and ingests vaccine, improving uniformity. Every vaccine line is monitored for concentration, flow, and nozzle performance because underdosing creates gaps, and overdosing wastes product and can stress chicks. Chicks are counted automatically at speed. Optical counters and weigh scales track chick numbers per box and average chick weight. And weight is a key quality indicator because it reflects embryo development, hydration status, and handling conditions. Boxes are stacked with airflow channels because chicks generate heat and CO even at rest. And overheating during staging can kill birds faster than cold exposure. Transport from hatchery to broiler. Farm is cold chain thinking applied to live animals. Chick trucks use controlled ventilation, temperature monitoring, and sometimes heating or cooling to keep the load within a narrow comfort zone. The target is to deliver chicks warm, hydrated, and active, because the first 48 hours on the farm largely determines growth trajectory and feed conversion later. Broiler raising in the US is built around integration and repeatability. The same company typically controls genetics, hatchery feed mill, veterinary programs, and processing plant, because tight control reduces variability. Farms operate on Allen, allout cycles. One flock goes in, grows, then the house is emptied, cleaned, and reset, breaking disease cycles and allowing the next flock to start in a low-pathogen environment. Before chicks arrive, the house is prepped like a climate chamber. Bedding, usually with shavings or rice hulls, is laid to manage moisture and provide insulation. Water lines are flushed and disinfected. Drinker height is set for chick size. And feed pans are staged to maximize early feed access. The air temperature is preheated, not just for comfort, but for physiology. Chicks cannot regulate body temperature well, so cold stress immediately reduces feeding and weakens immunity. Modern broiler houses are controlled by computer systems that manage heat, ventilation, humidity, and static pressure. Minimum ventilation runs even in cold weather to remove moisture and ammonia, because wet litter becomes a source of footpad burns and respiratory stress. In hot weather, tunnel ventilation takes over. Large exhaust fans pull air lengthwise through the house at high speed, creating wind chill across the birds. Many houses add evaporative cooling pads at the air inlets, where water evaporates to drop incoming air temperature. Trading water use for lower mortality during heat waves, sensors drive the entire system. Temperature probes, humidity sensors, and static pressure sensors feed a controller that adjusts fan staging, inlet opening, and heater output. The goal is stable air quality, because broilers grow fastest when they breathe clean air with low ammonia and low dust. Even airflow patterns matter. Dead zones create hot spots and wet litter. So house design includes baffles, inlet placement, and fan capacity matched to building length and stocking density. Lighting is programmed like a production parameter. LED systems reduce power use and allow precise dimming schedules that influence activity, feeding patterns, and leg health. Light intensity and photoperiod are tuned to encourage early feeding, then manage growth to reduce metabolic disorders. The house computer logs these settings. Because a change in lighting can show up later in weight uniformity and processing yield, water is one of the fastest indicators of flock health. Water meters track hourly consumption, and sudden drops or spikes can signal disease, temperature stress, or equipment failures before mortality rises. Drinkers are engineered to minimize leaks, because every drip becomes wet litter, and wet litter becomes ammonia. And ammonia becomes reduced growth and higher condemnations at processing. Feeding is an industrial logistics loop tied directly to growth curves. Feed is delivered from a mill into farm silos, then augers move it through feed lines into pans. Diet changes happen in phase: starter, grower, finisher, adjusting protein, energy, and amino acids to match bird growth and reduce waste nitrogen. Feed conversion ratio is the dominant metric: how many pounds of feed it takes to gain a pound of live weight. And small improvements in feed conversion translate into massive savings at national scale. Uniformity is managed with data and behavior control. Automatic weigh scales placed in the house record bird weights throughout the day, and the system can show whether birds are growing evenly or splitting into heavy and light groups. If uniformity slips, managers adjust ventilation, feeder space, or lighting patterns to push more birds to eat consistently. Because processing plants need predictable weights to maximize line efficiency and cut yields, health management is preventative and measurement. Biosecurity barriers limit visitors, control vehicle entry, and enforce clothing and footwear changes. Because the easiest disease to treat is the one that never enters the house. Litter quality is monitored because it's a health indicator. Dry, friable litter supports clean feet and lower ammonia. Ventilation settings are often adjusted specifically to keep litter moisture in a controlled range. Because the house is a moisture machine, birds exhale and excrete water continuously as broilers grow. Their heat output increases dramatically, and the ventilation system becomes the main tool for maintaining comfort. Heat stress can kill quickly because broilers dissipate heat poorly. So fans, cooling pads, and emergency backup power become life-critical infrastructure. Mega farms have alarm systems tied to phones and service networks. And generators are sized to run essential fans and controllers during grid failure. Because losing ventilation for minutes can be catastrophic at full grow-out weights. The grow-out period is short by design. Modern broilers reach market weight in weeks, not months, because genetics, nutrition, and environment are optimized for rapid muscle gain. That speed creates its own engineering constraints. High growth demands high oxygen, stable temperatures, and low stress. Or the birds convert feed into heat and inflammation instead of meat. Near the end of the cycle, processing plant requirements dictate schedules. Some farms thin flocks with partial harvests, removing heavier birds first to reduce density and allow remaining birds to finish. Catching is increasingly mechanized. Harvesting machines use conveyors and soft handling systems to load birds into modules, reducing labor and bruising. Bruising is not just a welfare issue. It's a yield loss and a trim cost at the plant. Transport to processing is managed under animal welfare and meat quality constraints. Modules are designed for airflow, and trucks are scheduled to minimize time in extreme weather. Stress before processing affects meat quality through biochemical changes. So the goal is calm handling, stable temperatures, and minimal waiting time at the plant. What makes this entire US broiler system mega and high-tech isn't one machine. It's the closed loop between biology and control systems. Hatcheries use temperature mapping, CO management, turning automation, and in ovo vaccination robotics to deliver uniform chicks. Farms use sensor-driven climate control, precise feed logistics, and continuous monitoring of water, weight, and air quality to convert feed into muscle efficiently. At this scale, a fraction of a degree in incubator temperature, a small humidity drift, or a subtle ventilation imbalance becomes visible as millions of dollars in performance. Which is why the modern chicken supply chain runs like an integrated manufacturing process, except the product is alive, growing, and constantly responding to every variable the system can measure and control.